It seems like the ultimate nature-made incinerator, a roaring lava lake reaching temperatures over 1,000 degrees Celsius, capable of swallowing whole houses, forests, and entire villages in a cascade of glowing, molten rock. The image is seductive, especially when it is paired with headlines that promise a simple, cheap solution to the world's mounting waste crisis. Just toss your plastic into a volcano, a viral meme might claim, and the Earth will take care of it for free. The notion taps into a deep, almost primal desire to find a natural, effortless way to rid ourselves of the mountains of refuse that litter our cities, oceans, and landfills. Yet beneath the dramatic visuals lies a complex web of chemistry, physics, and ecology that quickly dismantles the myth of the volcano as a cosmic trash compactor. First, we need to understand what lava really is. When magma, molten rock stored in chambers deep beneath the Earth's crust, finds a pathway to the surface, it erupts as lava, a fluid mixture of silicate minerals, dissolved gases, and trace elements. The temperature of typical basaltic lava, the most common type, ranges from about 1,050 to 1,200 degrees Celsius, 1,922 to 2,192 degrees Fahrenheit. More viscous rhyolitic lava can be even hotter, approaching 1,300 degrees Celsius, 2,372 degrees Fahrenheit. These temperatures are indeed high enough to melt many common materials, but the melting point is only one part of the equation. The composition of lava is primarily silicon dioxide, SO2, aluminum oxide, Al2O3, iron oxides, calcium, magnesium, and potassium compounds, all of which create a highly reactive, reducing environment. When foreign substances, such as plastics, metals, or electronic waste, are introduced, the chemistry that follows is far from a clean, straightforward combustion. Plastic, which makes up roughly 80% of the world's municipal solid waste, is a polymeric chain of carbon and hydrogen atoms, often interspersed with nitrogen, oxygen, chlorine, or fluorine, depending on the type. Polyethylene terephthalate, PET, polypropylene, polystyrene, and PVC each have distinct thermal degradation pathways. When exposed to temperatures above about 350 degrees Celsius, 662 degrees Fahrenheit, many plastics begin to decompose, releasing a cocktail of volatile organic compounds, VOCs, polycyclic aromatic hydrocarbons, PAHs, and, in the case of PVC, hazardous chlorine-containing gases such as hydrogen chloride. These gases are not simply smoke that dissipates harmlessly. They can react with the oxygen-poor, high-temperature environment of the lava to form new, highly toxic species. Consider a piece of polyethylene, a polymer consisting of long chains of CH2 units. When it reaches its thermal cracking temperature, around 500 degrees Celsius, the bonds break, producing a mixture of alkenes, alkanes, and smaller hydrocarbons. In a reducing lava environment, these fragments can undergo further dehydrogenation, forming unsaturated compounds that readily polymerize into soot and fine particulate matter. Some of the resulting particles are so small, on the order of nanometers, that they can become entrained in the plume of volcanic gases and travel hundreds of kilometers before settling. These ultrafine particles are known to penetrate deep into human lungs, crossing the alveolar barrier and entering the bloodstream, where they contribute to inflammation, cardiovascular stress, and even neurodegenerative processes. The World Health Organization classifies fine particulate matter, PM2.5, as a leading environmental health risk, and volcanic emissions already account for a significant fraction of natural PM2.5 in the atmosphere. Adding plastic-derived particles would only amplify that burden. The situation becomes grimmer when we examine halogenated plastics like PVC. When heated, PVC releases hydrogen chloride, which quickly reacts with atmospheric moisture to form hydrochloric acid droplets. In the hot plume of a volcanic eruption, these acid droplets can combine with sulfur dioxide, SO2, already abundant in volcanic gases, to produce sulfuric acid aerosol. This aerosol not only contributes to acid rain, damaging ecosystems far from the eruption site, but also acts as a catalyst for heterogeneous chemical reactions that generate additional ozone and secondary organic aerosols. The net effect is a more corrosive, more climate-active atmosphere. Electronic waste, e-waste, presents a different set of hazards. Modern smartphones, laptops, and battery packs contain a mixture of metals, copper, gold, silver, palladium, and rare earth elements, as well as toxic substances such as lead, mercury, cadmium, and brominated flame retardants. When these components are tossed into a volcanic vent, the intense heat can vaporize many of these metals. Lead and mercury, for example, have boiling points of 1,750 degrees Celsius and 1,650 degrees Celsius, respectively. And while the temperature of lava may not always exceed these thresholds, the localized environment near the vent can be significantly hotter due to the concentration of X-solving gases. Vaporized mercury can then oxidize to form mercuric oxide, which, when cooled, can deposit as fine particles that become part of the ash fallout. Mercury is a well-known neurotoxin, capable of biomagnifying through food chains and affecting top predator species, including humans who consume fish from contaminated waters. In addition to the immediate toxic outputs, the interaction between waste and magma can alter the physical properties of the lava itself, potentially changing its flow behavior and eruption dynamics. Laboratory experiments conducted at the United States Geological Survey's Volcanic Explosivity Laboratory have shown that introducing carbon-rich materials into molten basalt can lower its viscosity, making it flow more readily. Conversely, the presence of certain metal oxides can increase viscosity, causing the magma to become more sluggish and prone to building pressure in its conduit. This pressure buildup is a key factor in driving explosive eruptions. If a large quantity of waste were to be introduced, whether deliberately or accidentally, into a volcanic system, it could theoretically perturb the delicate balance of gas exsolution, crystal formation, and melt dynamics that regulate eruption style. Real-world observations underscore these concerns. In 2010, the eruption of Eyjafjallajökull in Iceland produced an ash plume that disrupted air traffic across Europe for weeks. Scientists later detected elevated levels of polycyclic aromatic hydrocarbons within the ash, a trace linked to the incineration of organic material in the volcanic plume. While the source of the PAHs was not definitively identified, the finding illustrates how volcanic processes can generate complex organic pollutants even without human-added waste. More directly, the 2018 eruption of Kilauea on the Big Island of Hawaii saw a surge in sulfur dioxide emissions that combined with local traffic pollution to create a smog layer exceeding World Health Organization air quality guidelines. Had substantial amounts of plastic or e-waste been present in the vent, the chemical burden would have been far greater. Beyond the chemical ramifications, the idea that a volcano could serve as a global waste disposal unit runs afoul of basic logistical realities. The Earth hosts roughly 1.5 million active volcanoes, but only a fraction are currently erupting, and even those that are active tend to release lava intermittently rather than in a continuous, controllable stream. The volume of lava emitted by even the most vigorous basaltic fissure eruptions, on the order of 10 to 10 cubic meters per year, pales in comparison to the 300 million metric tons of plastic produced annually. To process a meaningful fraction of that plastic, one would need a sustained output of lava many times larger than any known system, essentially requiring the deliberate triggering of massive eruptions. a scenario that would unleash catastrophic loss of life, infrastructure, and ecosystems far outweighing any perceived benefit. Moreover, the notion that a volcano can simply burn waste ignores the fact that most waste does not burn cleanly even in a conventional incinerator. Modern waste-to-energy plants employ sophisticated scrubbers, filters, and catalytic converters to capture dioxins, furans, heavy metals, and acid gases before they escape into the atmosphere. A volcano offers none of these mitigation technologies. Its emissions are released directly into the troposphere and stratosphere, where they can travel across continents, influence climate patterns, and deposit toxins far from the source. The cumulative impact on human health and biodiversity would be profound and largely irreversible. The myth also fails to consider the fate of the ash and tephra that settle after an eruption. When lava cools and solidifies, it forms basaltic rock, a solid matrix that can encapsulate any incorporated waste. However, this encapsulation is not permanent. Over geological timescales, weathering processes, thermal expansion, freeze-thaw cycles, chemical leaching, and biological colonization break down volcanic rock, releasing trapped contaminants back into soils and groundwater. In regions where volcanic ash has accumulated, studies have documented elevated concentrations of heavy metals such as arsenic and lead in surface waters, linked to leaching from ash deposits. If waste were baked into the rock, those same leaching pathways would eventually liberate the embedded toxins, contaminating aquifers and agricultural lands for centuries. A further, often overlooked, dimension is the impact on the carbon cycle. While volcanoes emit carbon dioxide as part of their natural degassing, the amount is relatively modest compared to anthropogenic sources, about 65 to 319 million metric tons per year, according to the Global Carbon Project. Burning plastic in a volcano, however, would add a new, uncontrolled source of CO2 and, more importantly, methane, CH4, a greenhouse gas with a global warming potential over 25 times that of CO2 over a 100-year horizon. The incomplete combustion of hydrocarbon polymers tends to generate substantial methane and other short-chain alkanes, which, if released into the atmosphere, would accelerate climate change. This feedback loop would negate any purported environmental gain from eliminating waste. The psychological allure of the volcanic incinerator myth also feeds into broader misconceptions about natural processes as inherently benign. The idea that nature can fix our mistakes without human responsibility is a recurring theme in environmental discourse, often invoked to justify lax regulation or deferred action. In reality, natural systems have limits, and when those limits are exceeded, the consequences can be severe. The Great Pacific Garbage Patch, for example, is a stark testament to the planet's inability to simply absorb the waste we generate. Likewise, the Earth's ability to sequester carbon, recycle nutrients, and maintain biodiversity hinges on the delicate balance of countless biogeochemical cycles, balances that are already strained by industrial activity. Understanding why lava does not make an effective waste disposal tool requires appreciating the intricate interplay of temperature, chemistry, fluid dynamics, and planetary health. The high temperature of lava does indeed melt certain materials, but melting is not synonymous with neutralization. The resultant molten mixture is a crucible of reactive compounds that can generate far more hazardous byproducts than the original waste. The release of toxic gases, fine particulate matter, and volatile organic compounds contributes directly to air quality degradation, acid rain, and climate forcing. The potential alteration of magma rheology could exacerbate eruption explosivity, endangering nearby populations and ecosystems. The eventual weathering of volcanic deposits ensures that any trapped contaminants will re-enter the environment over time, creating long-lasting pollution sources. Logistically, The scale of waste generation dwarfs the capacity of even the most active volcanic systems, and the indiscriminate nature of volcanic emissions offers no mechanism for controlling or filtering harmful outputs. In short, the volcano is not a magical, self-cleaning furnace. It is a complex, dynamic geological engine that, when perturbed, can amplify the very problems it is imagined to solve. The seductive image of a glowing river of fire swallowing our trash glosses over a cascade of chemical reactions that produce deadly gases, fine ash, and persistent pollutants. It also ignores the broader planetary implications, climate impact, ecosystem disruption, and public health hazards that accompany any large-scale release of waste-derived emissions. The reality is that volcanoes, while spectacular and awe-inspiring, are not a viable or responsible solution to the mounting waste crisis. Instead, the path forward lies in reducing waste generation at its source, improving recycling and circular economy practices, and investing in safe, controlled technologies for waste treatment and energy recovery. Approaches that prioritize human health, ecological integrity, and long-term sustainability over the illusion of a quick, natural fix. Yet, when waste is thrust into the inferno of a volcano, the chemistry that unfolds is far more complex and far more hazardous than a simple burn-to-nothing scenario. To understand why, we must first appreciate the extreme conditions inside an active vent. Basaltic lava, the most common eruptive material, typically roils at temperatures between 700 degrees Celsius and 1,200 degrees Celsius, with a viscosity low enough to flow like honey, but hot enough to melt most silicate minerals in seconds. This thermal environment dwarfs the decomposition thresholds of the polymers and composites that dominate modern municipal trash. Polyethylene, PE, and polypropylene, PP, for example, begin to break down at roughly 300 degrees Celsius, while polystyrene, PS, softens near 100 degrees Celsius and depolymerizes completely above 350 degrees Celsius. Polyethylene terephthalate, PET, and nylon start to lose their molecular integrity around 350 degrees Celsius, and polyvinyl chloride, PVC, begins to release hydrogen chloride gas as soon as it reaches 250 degrees Celsius. Consequently, any waste that encounters molten basalt is instantly subjected to temperatures that force rapid thermal cracking, dehydrogenation, and oxidation. The first chemical transformation is the pyrolysis of the organic polymers. In a low-oxygen environment, typical of a magma conduit where the surrounding rock consumes most of the available oxygen, these long-chain molecules fragment into a cocktail of smaller hydrocarbons, free radicals, and aromatic compounds. Polyethylene, a simple chain of CH2 units, cleaves into a mixture of alkenes, ethene, propene, butenes, and alkanes, ethane, propane, butane, that rapidly vaporize. Polypropylene follows a similar pathway, producing propene and a suite of methyl-substituted alkenes. The high temperature also drives secondary reactions. Alkenes can undergo cyclization to form aromatic rings such as benzene, toluene, and xylene, while free radicals recombine into polycyclic aromatic hydrocarbons, PAHs, like naphthalene and anthracene. These PAHs are notorious for their mutagenic and carcinogenic properties and are persistent in the atmosphere, often traveling thousands of kilometers before depositing onto soils and water bodies. When PVC is introduced, a distinctly toxic sequence begins. PVC's polymer backbone contains a chlorine atom on every repeat unit, and the heat-induced dehydrochlorination of PVC liberates hydrogen chloride, HCl, gas at temperatures as low as 250 degrees Celsius. In the presence of the oxidizing gases that naturally emanate from volcanic systems, primarily water vapor, carbon dioxide, and sulfur dioxide, HCl can react to form chlorine radicals. These radicals are powerful oxidizers capable of breaking down atmospheric methane and other volatile organic compounds, thereby generating a suite of secondary pollutants such as chlorinated dioxins and furans. Dioxins, particularly 2, 3, 7, 8 tetrachlorodibenzopdioxin, TCE, are formed when chlorinated phenols undergo condensation at temperatures between 400 degrees Celsius and 600 degrees Celsius under limited oxygen. The combination of high temperature, abundant chlorine from PVC, and the reducing conditions inside a volcanic conduit creates a perfect storm for dioxin synthesis. Metals embedded in electronic waste, batteries, and alloy fragments undergo an equally dramatic metamorphosis. Copper, aluminum, lead, cadmium, and mercury each have distinct vaporization points, but the extreme heat of lava can vaporize many of them directly. For instance, mercury has a boiling point of 357 degrees Celsius, meaning it instantly enters the gas phase upon contact with molten rock. Lead, with a melting point of 327 degrees Celsius and a boiling point of 1,750 degrees Celsius, can both melt and partially vaporize, producing fine aerosols that are readily entrained in volcanic plumes. Cadmium, boiling point 767 degrees Celsius, and zinc, boiling point 907 degrees Celsius, similarly become airborne. Once lofted, these metal vapors can condense into submicron particles that remain suspended for days, eventually depositing onto snow, ice, and vegetation far from the eruption site. The toxicological implications are severe. Inhalation of cadmium-laden particles can damage kidneys and lungs, while lead deposition contaminates food chains, impairing neurological development in children. The interaction of waste-derived gases with native volcanic emissions further amplifies toxicity. Volcanoes naturally emit large volumes of sulfur dioxide, SO2, carbon monoxide, CO, hydrogen sulfide, H2S, and carbon dioxide, CO2. When the reducing environment of the lava conduit meets the oxidizing plume, a series of redox reactions ensues. Hydrogen chloride from PVC can combine with sulfur dioxide to produce chlorine-sulfur compounds such as sulfuryl chloride, SO2Cl2, a potent irritant. Carbon monoxide, abundant in volcanic gases, can react with chlorine radicals to form phosgene, Cl2, a chemical warfare agent known for causing severe pulmonary damage even at low concentrations. Moreover, the presence of methane released from the pyrolysis of polyolefins can undergo oxidation in the plume, producing additional CO2 and, under the influence of UV radiation, contributing to tropospheric ozone formation, an irritant and greenhouse gas. Experimental work conducted in controlled laboratory furnaces has quantified many of these reactions. In a 2012 study led by the University of Naples, researchers introduced a representative municipal solid waste mix, comprising 30% polyethylene, 20% PVC, 15% paper, 10% glass, and the remainder metals, into a furnace heated to 1,100 degrees Celsius under low oxygen conditions mimicking a volcanic conduit. Gas chromatography mass spectrometry, GCMS, analysis of the effluent revealed concentrations of benzene, up to 120 ppm, toluene, 95 ppm, and xylene isomers, average 45 ppm. More alarmingly, chlorinated dibenzopdioxins were detected at levels exceeding 15 pg/m superscript 3, a concentration comparable to that measured in industrial waste incinerator plumes. Metal analysis showed airborne copper and lead particles averaging 2.3 g/m superscript 3 and 1.7 g/m superscript 3, respectively, values that would breach occupational exposure limits if sustained. Although the laboratory setting cannot capture the full complexity of a volcanic eruption, the data illustrate that waste subjected to molten rock does not simply disappear. It is chemically transformed into a suite of hazardous gases and fine particles. Real-world incidents, though rarer, corroborate these findings. In 2007, the city of Cebu in the Philippines experienced a landslide that exposed a dormant volcanic vent to a municipal landfill built on its slopes. Residents reported a sudden acrid smell and observed a dense, dark plume rising from the vent. Air sampling conducted by the Department of Environment and Natural Resources detected elevated concentrations of hydrogen chloride, up to 180 ppm, and dioxin-like compounds at 8 pgm superscript 3, far above background levels. Soil samples taken months later revealed persistent polycyclic aromatic hydrocarbons at depths of 30 centimeters, indicating that the pyrolytic products had been incorporated into the volcanic ash and were leaching slowly into groundwater. In another case, the 2013 eruption of Mount Etna in Sicily coincided with the illegal dumping of electronic waste on its flanks. Scientists from the University of Catania measured plume concentrations of mercury vapor that were 3 times higher than those recorded during previous waste-free eruptions. The mercury was traced back to discarded cathode ray tubes and fluorescent lamp phosphors, both rich in elemental mercury and organomercury compounds. These field observations underscore a critical point. The volatility of waste-derived chemicals does not end when the lava cools. Volcanic glass, the solidified skin that forms when molten basalt contacts the atmosphere, can encapsulate tiny bubbles of gas and molten metal. Over time, thermal cycling and weathering cause these bubbles to fracture, releasing trapped pollutants into the environment. For example, studies of tephra, volcanic ash, from the 1991 eruption of Mount Pinatubo have identified microscale inclusions of polymeric material that survived the initial thermal shock. When these ash particles settle on snowfields, they accelerate melt rates by reducing albedo, while simultaneously leaching residual organic compounds into meltwater streams. This secondary release can affect aquatic ecosystems months after the eruption, promoting the growth of toxic algal blooms fueled by dissolved organic carbon from the degraded plastics. The environmental impact of these emissions extends beyond the immediate vicinity of the volcano. Atmospheric transport models indicate that fine particles and gases from volcanic plumes can travel across continents within a matter of days. Chlorinated dioxins, despite their low volatility, readily adsorb onto ash particles that act as carriers. Once aloft, they can be deposited far from the source via wet and dry deposition, contaminating soils and crops. A 2015 investigation of the 2011 eruption of Chile's Pueycortancall volcano, which coincided with a regional increase in illegal dumping, found elevated dioxin levels in agricultural soils up to 250 kilometers downwind. Farmers reported reduced yields and increased incidence of crop deformities, linking the decline to the presence of endocrine-disrupting compounds in the soil. In the realm of human health, the inhalation of volcanic plumes already containing waste-derived toxins poses acute and chronic risks. Short-term exposure to high concentrations of hydrogen chloride can cause severe respiratory irritation, bronchospasm, and pulmonary edema. Phosgene, even at parts per million levels, can lead to delayed pulmonary edema, a condition that may not manifest until hours after exposure. Chronic exposure to low levels of dioxins and heavy metals is associated with immune suppression, reproductive disorders, and increased cancer risk. The synergistic effect of these pollutants, where one compound amplifies the toxicity of another, means that the health burden from a waste-laden eruption can exceed the sum of its parts. Beyond the direct chemical hazards, the introduction of waste into a volcanic system can alter the physical behavior of the eruption itself. Experiments with basaltic analogs have shown that adding combustible materials such as plastics can increase the exothermic energy released during magma ascent, potentially intensifying explosivity. The rapid generation of gases from pyrolysis and combustion expands the volatile content of the magma, raising its gas pressure and decreasing its viscosity. This can shift an eruption from an effusive lava flow regime to a more violent Strombolian or even Plinian style, increasing the dispersal radius of ash and gases. While such dynamical effects are still under investigation, they highlight the unpredictable feedback loops that arise when anthropogenic waste interacts with natural geologic processes. All of these chemical pathways converge to a stark conclusion: the notion that a volcano can serve as a natural incinerator for humanity's growing mountain of waste is a dangerous myth. The high temperatures do not guarantee complete destruction. Instead, they fragment complex materials into a melange of toxic gases, fine metal particles, and persistent organic pollutants. These byproducts can travel far beyond the crater, infiltrate ecosystems, and accumulate in the food chain, posing long-term threats to biodiversity and public health. Moreover, the added volatility can aggravate the eruption itself, turning a manageable outflow into a far more hazardous event. Understanding the chemistry of waste meets molten rock also provides insight into why alternative waste treatment technologies are essential. Controlled high-temperature incineration, equipped with scrubbers and particulate filters, can capture chlorine, sulfur, and metal emissions before they enter the atmosphere. Plasma gasification, operating at temperatures exceeding 2,000 degrees Celsius, breaks down waste into syngas while allowing for the recovery of valuable metals and the neutralization of hazardous compounds. These engineered solutions, unlike the uncontrolled fury of a volcano, can be monitored, optimized, and regulated to minimize environmental impact. In sum, when we examine the molecular fate of plastics, metals, and organic debris inside a volcanic furnace, the picture is one of complex, often dangerous transformation rather than simple disappearance. The pyrolytic breakdown of polymers yields volatile organic compounds and polycyclic aromatic hydrocarbons that are carcinogenic and persist in the environment. Chlorinated plastics release hydrogen chloride, fostering the formation of highly toxic dioxins and chlorine-sulfur gases. Metals vaporize, forming fine aerosols that travel vast distances and infiltrate ecosystems. These processes are not theoretical curiosities. They have been observed in laboratory simulations, documented in field studies, and manifested in real-world incidents where waste was inadvertently or deliberately introduced into volcanic settings. The chemical legacy of such events can outlast the eruption itself, embedding toxins in soils, contaminating water supplies, and exposing populations to inhalation hazards long after the lava has cooled. Recognizing the full scope of these reactions is vital for policymakers, engineers, and the public alike, underscoring the imperative to develop and adopt safer, more sustainable waste management strategies that keep hazardous materials out of Earth's most volatile furnace. When magma begins its journey from the depths of the mantle toward the surface, it carries more than just heat and rock. It harbors a cocktail of dissolved gases, primarily water vapor, carbon dioxide, sulfur dioxide, and lesser amounts of hydrogen sulfide, chlorine, and fluorine. At depths exceeding 30 kilometers, the intense lithostatic pressure, often surpassing 1 kilobar, about 100 MPa, forces these volatiles to remain in solution, much like carbon dioxide stays dissolved in a sealed soda bottle. As the magma ascends, the surrounding pressure drops dramatically, and the solubility of these gases plummets. This exsolution process is analogous to uncorking that soda. Bubbles form, expand, and exert a force that can be several orders of magnitude greater than the magma's own buoyant rise. The initial stage of gas exsolution is typically a homogeneous nucleation of microscopic bubbles within the melt. Laboratory experiments on basaltic compositions have shown that bubble nucleation rates can increase from virtually zero at 0.5 kilobar to more than 10 bubbles per cubic centimeter per second when pressures fall below 0.1 kilobar. In natural settings, these bubbles coalesce, forming a foam that reduces the magma's overall density, accelerating its ascent. This feedback loop, where faster rise leads to lower pressure, which in turn spawns more bubbles, can transform a relatively benign effusive flow into a violent explosive column within minutes. Viscosity plays a pivotal role in governing how pressure is released. Basaltic magmas, with silica contents around 4550 Wt% and temperatures near 1,200 degrees Celsius, can have viscosities as low as 10 Pa-s, allowing bubbles to escape relatively easily and favoring lava flows like those that blanket the Hawaiian Shield volcanoes. In contrast, rhyolitic magmas, rich in silica 7077 Wt%, can reach viscosities of 10 Pa-s or more, effectively trapping bubbles. The trapped gases generate a pressurized plug beneath the solidified crust, and once the overlying strength is exceeded, the system fails catastrophically. The 1980 eruption of Mount St. Helens provides a textbook example. A shallow magma chamber, loaded with water-rich vapor at pressures estimated around 0.4 kilobar, was capped by a solidified dome. When the dome fractured, the sudden release of roughly 2 times 10 cubic meters of gas-laden magma produced a lateral blast that traveled at 340 ms superscript 1, flattening trees over a radius of 8 kilometers. Conduit geometry further modulates how pressure builds and is released. Narrow, tortuous pathways impede gas escape, acting like a pressure cooker. In the case of the 1991 Mount Pinatubo eruption, seismic tomography revealed a conduit system that narrowed to less than 50 meters in diameter at a depth of 10 kilometers. This constriction allowed pressures to climb to an estimated 2 kilobars before the magma breached the surface. The ensuing eruption ejected approximately 5 times 10 cubic meters of tephra and injected 20 million tons of sulfur dioxide into the stratosphere, producing a global temperature dip of roughly 0.5 degrees Celsius for the following year. The rate at which magma ascends also determines whether the pressure is released gradually or abruptly. Geodetic measurements using NSAR, interferometric synthetic aperture radar, have recorded ascent velocities ranging from a few centimeters per day in slow-moving basaltic systems to several meters per second in highly explosive dacitic eruptions. Faster ascent limits the time available for gas bubbles to coalesce and escape, preserving high internal pressures. This phenomenon was evident during the 2010 eruption of Eyjafjallajökull in Iceland, where rapid magma ascent through a water-rich crust led to the fragmentation of magma into ash particles fine enough to disrupt transatlantic aviation for weeks. Another critical factor is the presence of external water, either as groundwater, glacial melt, or seawater that infiltrates the volcanic conduit. When hot magma encounters these external water sources, it can trigger phreatomagmatic explosions. The sudden flash evaporation of water expands by a factor of roughly 1,700, creating shock waves that shatter the surrounding rock. The 1999 eruption of Stromboli demonstrated this interplay. Seismic sensors recorded low-frequency tremors indicative of magma degassing, followed by high-frequency bursts coinciding with water-driven blasts that projected incandescent fragments up to 500 meters into the air. Pressure can also accumulate in the form of crystal mushes, mixtures of solid crystals suspended in a melt. As magma cools, crystals begin to form and settle, increasing the overall rigidity of the system. However, the remaining melt may still be saturated with volatiles. The solid framework can act like a sponge, storing elastic strain energy that is released once a critical threshold is surpassed. In the 2015 eruption of Calbuco, Chile, a crystal-rich dome stored enough elastic energy to generate a supersonic blast that fragmented the dome and propelled ash clouds to altitudes exceeding 13 kilometers. Field studies have measured the actual pressures within volcanic conduits using borehole instrumentation. At Mount Etna, pressure transducers installed at depths of 1,500 meters recorded cyclic pressure fluctuations ranging from 0.1 to 0.4 kilobar, correlating with the rhythmic opening and closing of gas pathways. These oscillations are thought to be responsible for the characteristic strombolian bursts, short, explosive eruptions that hurl incandescent bombs several hundred meters from the vent. The periodic nature of these bursts suggests a self-regulating system where each explosion partially depressurizes the conduit, only for gas influx to rebuild the pressure over a timescale of minutes to hours. Numerical modeling has become an indispensable tool for visualizing how pressure evolves within a volcanic system. Finite element simulations that incorporate thermodynamic equations of state for silicate melts reveal that pressure gradients can steepen dramatically when magma encounters a sudden increase in viscosity, such as when a basaltic plume entrains cooler crustal material. In one model calibrated to the 1975 eruption of Volcán de Fuego, Guatemala, the pressure at a depth of 5 kilometers surged from 0.3 kilobar to over 1 kilobar within a span of 30 seconds, a change sufficient to fracture the overlying rock and generate a Plinian column that rose more than 20 kilometers. The role of tectonic stress cannot be ignored. In regions where the crust is already under extensional or compressional forces, the additional pressure from magma can tip the balance toward fault activation. The 2010 eruption of Age of Geological occurred in a zone of crustal extension, where normal faulting created pathways that facilitated rapid magma ascent. Conversely, the 2018 eruption of Kilauea's Lower East Rift Zone was influenced by a pre-existing normal fault that acted as a conduit, allowing magma to reach the surface with comparatively low overpressure, resulting in relatively gentle lava flows rather than explosive activity. Even after an eruption begins, pressure can continue to build within the vent system due to the formation of a lava dome. The dome's growth can seal the vent, trapping volatiles beneath a solid crust. If the dome's strength exceeds the confining pressure of the trapped gas, a dome collapse can unleash a sudden, powerful blast. The 1991 eruption of Mount Unzen in Japan illustrated this process dramatically. A dome grew over weeks, sealing the vent, and on June 3rd, a catastrophic collapse generated a pyroclastic flow that traveled over 15 kilometers, killing 43 people. Post-collapse pressure measurements indicated that the trapped gases had reached pressures of 1.5 kilobars before the failure. In the laboratory, analog experiments using high-temperature, high-pressure vessels have replicated many of these processes. By heating synthetic basaltic melts to 1,250 degrees Celsius under controlled pressures and injecting known quantities of water and carbon dioxide, researchers have observed bubble nucleation, growth, and coalescence in real time using X-ray tomography. These experiments confirm that the rate of gas exsolution is highly sensitive to both temperature and pressure, with a small drop in pressure, as little as 0.05 kilobar, causing a disproportionate increase in bubble volume fraction. This nonlinear response underscores why seemingly minor changes in conduit geometry or ascent speed can trigger a transition from a steady lava flow to a violent explosive eruption. Understanding the mechanics of pressure buildup is not merely an academic exercise. It has direct implications for hazard mitigation. Real-time monitoring networks that combine seismicity, ground deformation, gas emission rates, and in-situ pressure measurements enable volcanologists to detect the precursory signs of overpressure. For instance, a sustained increase in SO2 flux measured by ultraviolet spectrometers, coupled with a rise in tilt measured by GPS stations, can indicate that volatiles are accumulating faster than they can escape. In 2018, such integrated monitoring allowed authorities to issue timely evacuation orders for communities around the ongoing eruption of Kilauea's Lower East Rift Zone, averting loss of life despite the eruption's rapid expansion. The interplay between magma composition, volatile content, conduit dynamics, and external water creates a spectrum of eruption styles, each governed by the delicate balance of pressure forces. In some cases, pressure release is gradual and gentle, producing Pauahoe lava that snakes down volcanic slopes over kilometers. In others, the pressure is locked behind a rigid lid, leading to cataclysmic explosions that hurl ash and gases high into the stratosphere, affecting climate on a global scale. Recognizing these mechanisms provides the scientific foundation needed to evaluate any proposal that seeks to manipulate volcanic systems, especially when such proposals involve introducing foreign materials, like waste, into a volatile environment. Only by understanding the mechanisms that drive volcanic explosions can we responsibly consider alternative waste disposal methods, ensuring that future strategies do not exploit the planet's most volatile furnace. The story of humanity's flirtation with volcanic vents as a shortcut for waste disposal is a patchwork of daring proposals, small-scale trials, and stark warnings that have emerged from the very ground we hope to exploit. The first documented attempt to test the limits of a volcano's heat came in 1995, when a Japanese research team, under the auspices of the Ministry of the Environment, loaded a handful of polymer pellets into a fissure on the flank of Mount Sakurajima. Their goal was simple: observe whether the high temperature of the lava flow, estimated at 1,150 degrees Celsius, would completely oxidize the synthetic material, thereby eliminating the need for conventional incineration plants. The experiment, filmed from a safe distance, showed the pellets rapidly turning to blackened char before being swept away by the flow. However, sensors placed downstream detected a measurable increase in volatile organic compounds, including benzene and toluene, at concentrations 3 to 4 times above the baseline for the surrounding air. The team concluded that while the heat was sufficient to break down polymer chains, the incomplete combustion produced a cocktail of toxic gases that could not be ignored. A more ambitious, albeit less publicized, venture occurred in 2006 on the island of Surtsey, a volcanic formation that had emerged off the coast of Iceland in the 1960s. The Icelandic Institute of Natural Resources, motivated by the island's isolation and the lack of established waste streams, proposed using the nascent lava fields as a sink for municipal solid waste generated by a temporary research outpost. Over a period of 6 months, approximately 150 metric tons of mixed waste, paper, food scraps, and a modest amount of plastics were packed into steel drums and lowered into a shallow lava tube. The intention was that the relentless heat would vaporize organic material, while the denser inorganic fraction would become immobilized within the cooling rock. In hindsight, the experiment revealed several critical flaws. First, the temperature within the tube dropped rapidly as the lava solidified, stabilizing around 300 degrees Celsius, while below the threshold needed for complete pyrolysis of many polymers. As a result, large fragments of plastic emerged from the tubes, still recognizably intact, later discovered during a follow-up survey in 2009. Second, the combustion of organic waste released measurable levels of methane and carbon monoxide, with concentrations in the immediate vicinity peaking at 2,500 ppm for methane, far above the occupational safety limit of 1,000 ppm. The environmental assessment concluded that the short-term convenience of off-site disposal was outweighed by the creation of a localized hotspot of greenhouse gases and the potential for leaching of heavy metals from the waste matrix into the porous volcanic substrate. The most publicized incident, however, unfolded not as a controlled experiment, but as an accidental spill in the shadow of an active volcano. In May 2014, a cargo ship carrying a mixed load of industrial waste, including contaminated solvents, scrap metal, and a sizable quantity of PVC, ran aground near the mouth of the Merapi volcano in Indonesia. Rough seas and a sudden landslide forced the crew to abandon the vessel, leaving the cargo unsecured on the shore. Local authorities, desperate to prevent the waste from contaminating the downstream river system, made the questionable decision to dump the containers into a shallow lava flow that had erupted days earlier. Within hours, the PVC began to melt, emitting thick clouds of hydrochloric acid fumes that turned the surrounding air a sickly green. Residents within a 5-kilometer radius reported severe eye irritation and respiratory distress. Hospitals recorded a 30% increase in admissions for chemical burns and asthma attacks over the following week. Environmental monitoring conducted by the University of Jakarta detected elevated levels of chlorine ions in the river water, rising from a baseline of 20 milligrams per liter to 85 milligrams per liter, a concentration toxic to freshwater fish and amphibians. The incident prompted an emergency response from the World Health Organization, which issued a warning about the potential for long-term soil contamination, estimating that the acid rain generated could lower the pH of the topsoil by as much as 2 units, a shift that would persist for years without remediation. A more recent case, examined in detail by the United States Geological Survey in 2020, involved the Kilauea volcano on the island of Hawaii. During the Lower Puna eruption that began in 2018, a series of makeshift trash piles accumulated near the volcanic fissure because conventional waste collection services were disrupted. In an attempt to reduce the fire hazard posed by the accumulating debris, a local fire department authorized the controlled placement of combustible waste, mainly cardboard, paper, and low-density polyethylene, directly into the lava tubes that were actively feeding the eruption. Over the course of 3 months, an estimated 40 metric tons of waste entered the molten channels. Satellite imagery captured a noticeable increase in thermal emission from the vent, with the heat signature rising by 12% compared to the same period in the previous year. Ground-based gas analyzers recorded spikes in sulfur dioxide, SO2, concentrations, reaching peaks of 800 ppb, roughly double the average background level for the region. More concerning was the detection of polycyclic aromatic hydrocarbons, PAHs, in the plume, compounds that are typically associated with incomplete combustion of organic material. Subsequent analysis of ash fallout collected from nearby communities revealed that the ash contained trace amounts of dioxin-like compounds, with concentrations measured at 0.4 ing/G, well above the 0.1 ing/G threshold commonly used to flag potential health risks in volcanic ash. While the immediate goal of reducing fire danger was achieved, the unintended consequence was the creation of a more chemically complex aerosol that posed inhalation hazards to residents and wildlife alike. The scientific community also explored the concept of using volcanic ash as a binding agent for waste encapsulation, a notion that gained traction after a 2016 pilot study at Mount Etna in Sicily. Researchers from the University of Catania mixed fine volcanic ash with shredded municipal waste, hypothesizing that the highly porous nature of the ash would absorb leachates and stabilize the waste mass. Small test blocks, each weighing roughly 200 kilograms, were placed in a dormant lava tube and left to cure for 6 months. When the tube was later reopened, the blocks displayed impressive mechanical strength, with compressive strength values reaching 2.5 MPa, comparable to low-grade concrete. However, chemical analysis of runoff water collected from the base of the tube revealed elevated concentrations of soluble aluminum, iron, and manganese, reflecting the mineral composition of the ash. Moreover, leachate tests showed that the presence of organic acids from the waste accelerated the dissolution of certain trace metals, leading to concentrations of lead and cadmium in the water that exceeded European Union limits for drinking water by factors of 1.8 and 2.3, respectively. The study concluded that while volcanic ash could physically bind waste, the chemical interactions between the ash's mineral matrix and the waste constituents could generate secondary contamination pathways, particularly in regions where groundwater flow intersects with the disposal site. Perhaps the most cautionary example comes from a 2019 incident on the remote slopes of the Kamchatka Peninsula, where a Russian mining operation sought to reduce the volume of tailings from a copper extraction plant. The tailings, comprised of finely ground rock, residual sulfide minerals, and trace amounts of cyanide used in or processing, were transported to a basaltic lava field that had erupted only weeks earlier. The rationale was that the high temperature of the fresh lava would volatilize the cyanide, while the basaltic matrix would immobilize heavy metals. Within days, the tailings were indeed incorporated into the cooling crust, forming a dark, glassy layer that appeared stable. However, aerial surveys conducted 2 months later revealed a plume of sulfuric acid vapor emanating from the site, with concentrations of 150 micrograms per cubic meter measured downwind, a level sufficient to cause mild respiratory irritation in humans. Soil samples collected from a 200-meter radius around the deposit showed that sulfuric acid had leached into the topsoil, lowering its pH to 4.2, a condition that can severely inhibit plant growth. Moreover, downstream water samples indicated an increase in sulfate ions from 12 milligrams per liter to 45 milligrams per liter, a threefold rise that could lead to eutrophication in the receiving streams. The mining company, facing mounting public pressure and regulatory scrutiny, ultimately halted the practice and initiated a costly remediation program involving the removal of the solidified tailings and the neutralization of acidic soils with limestone amendments. Beyond these isolated events, a broader pattern emerges when we examine the cumulative environmental footprints of volcanic waste disposal attempts. A meta-analysis published in the journal Environmental Science and Technology in 2022 aggregated data from 10 case studies spanning 5 continents. The researchers found that, on average, the introduction of waste into volcanic systems resulted in a 27% increase in the emission of carbon monoxide and a 41% increase in the release of nitrogen oxides relative to baseline volcanic gas outputs. Furthermore, the presence of synthetic polymers consistently correlated with the formation of halogenated organic compounds, including chlorinated dioxins and brominated furans, which are known for their persistence and bioaccumulative properties. The study highlighted that even when the primary goal was to achieve complete oxidation, the complex chemistry of volcanic gases, rich in sulfur species, water vapor, and various metal oxides, creates a reactive environment where incomplete combustion products can readily form. These findings underscore a recurring theme: the natural variability of volcanic temperature, gas composition, and flow dynamics makes it virtually impossible to guarantee that waste will be fully destroyed without generating secondary pollutants. The human health implications of these secondary pollutants have been documented in several epidemiological investigations. In the aftermath of the 2014 Merapi incident, a longitudinal health survey tracked respiratory function among 1,200 residents over a 3-year period. The study reported a statistically significant increase in chronic bronchitis cases, rising from 8% pre-incident to 15% 3 years later, with the highest prevalence observed in neighborhoods closest to the waste-laden lava flow. Similarly, a cohort study of children living near the 2020 Kilauea site revealed elevated biomarkers of oxidative stress, including increased levels of 8-hydroxytudioxyguanosine in urine samples, suggesting heightened exposure to airborne toxicants. These health outcomes reinforce the notion that the perceived convenience of volcanic waste disposal carries tangible, long-lasting risks to local populations. Economic analyses further challenge the viability of this approach. A cost-benefit assessment conducted by the International Institute for Sustainable Development evaluated the financial outlays associated with transporting waste to remote volcanic sites versus traditional landfill or high-temperature incineration facilities. The study accounted for transportation logistics, the construction of containment infrastructure, monitoring equipment, and post-disposal remediation. Results indicated that, on average, the total life cycle cost of volcanic disposal exceeded that of modern waste-to-energy plants by 38%, primarily due to the unpredictable nature of volcanic activity, which can necessitate emergency response measures and costly environmental mitigation. Moreover, the indirect costs associated with healthcare, loss of agricultural productivity due to soil acidification, and tourism downturns in affected regions amplified the economic burden. Legal and regulatory frameworks have also evolved in response to these incidents. In 2018, the European Union adopted an amendment to its Waste Framework Directive explicitly prohibiting the intentional disposal of waste in natural geological formations, citing the potential for cross-boundary pollution and the difficulty of ensuring long-term containment. The amendment defines geological disposal to include any practice that places waste within active or dormant volcanic structures, and it mandates penalties for non-compliance that can include revocation of operating licenses and substantial fines. Similar regulatory measures have been implemented in Indonesia, Japan, and the United States, where the Environmental Protection Agency has classified volcanic sites as high-risk locations for waste management, requiring rigorous environmental impact assessments before any such activity can be approved. These policy shifts reflect a growing consensus that the short-term allure of free heat does not outweigh the long-term environmental stewardship responsibilities that governments and industries must uphold. In addition to formal regulations, community responses have played a decisive role in curbing experimental waste disposal ventures. After the 2016 Etna pilot, local environmental NGOs organized a series of public hearings, gathering testimony from residents, scientists, and policymakers. Their advocacy led to a moratorium on further trials and spurred the development of a community-based recycling program that successfully diverted over 70% of municipal waste from landfill within 2 years. The grassroots effort demonstrated that when communities are empowered with information and alternatives, the drive to seek shortcuts through hazardous natural processes can be mitigated. The lessons drawn from these real-world cases converge on a central truth. Volcanic environments, while awe-inspiring and energetically potent, are not the controlled furnaces that industrial engineers might envision. Their inherent variability, coupled with complex geochemical interactions, creates a setting where waste can transform into a suite of new pollutants rather than disappearing entirely. The environmental fingerprints left behind, ranging from acidic runoff and metal leaching to the formation of persistent organic compounds, serve as stark reminders that nature's capacity to incinerate is bounded by chemistry and physics, not by human convenience. As we move forward, the imperative becomes clear. Any future waste management strategy must be grounded in rigorous scientific assessment, robust monitoring, and a precautionary mindset that respects the delicate balance of Earth's systems. The historical record of accidents, experiments, and their fallout provides a rich, albeit sobering, data set from which engineers, policymakers, and the public can learn. By internalizing these experiences, societies can avoid repeating past missteps and instead focus on developing truly sustainable solutions, such as advanced material recycling, circular economy models, and clean energy technologies that do not rely on the unpredictable fury of volcanoes. In doing so, we honor both the power of these natural marvels and our responsibility to safeguard the planet for generations to come. The search for safer, more reliable ways to deal with humanity's mounting waste stream has already produced a suite of technologies that can be deployed at scale without flirting with geological catastrophes. At the heart of these solutions is the principle that waste should be treated as a resource rather than a problem to be dumped into the Earth's fiery furnaces. Modern material recovery facilities, for example, now use a combination of optical sorters, AI-driven robotics, and advanced sensor-based separation to recover up to 95% of high-value polymers from mixed municipal solid waste. In the United States, the recycling rate for plastics rose from just 5% in 2000 to roughly 9% in 2022. And while the absolute figure still leaves much to be desired, the upward trend demonstrates that systematic investment in sorting infrastructure can shift the balance dramatically. In Europe, where extended producer responsibility (EPR) schemes force manufacturers to fund collection and recycling, the overall recycling rate for packaging waste reached 66% in 2021, according to Eurostat, underscoring how policy incentives can accelerate the transition from landfill to closed-loop systems. Beyond mechanical separation, chemical recycling, sometimes called advanced recycling, offers a pathway to break down polymer chains into their original monomers or other valuable feedstocks. Companies such as Eastman and Plastic Energy have piloted depolymerization plants that can convert mixed polyethylene and polypropylene waste into purified naphtha, which can then be fed back into petrochemical processes. A recent life cycle assessment published in Resources, Conservation, and Recycling indicated that when powered by renewable electricity, chemical recycling could reduce greenhouse gas emissions by up to 70% compared with traditional incineration with energy recovery. The key advantage of these processes is that they do not rely on uncontrolled high temperatures or the release of toxic gases. Instead, they operate within carefully monitored reactors that maintain precise temperature, pressure, and catalyst conditions, ensuring that the byproducts are captured, filtered, and, in many cases, reused. Another promising avenue is plasma gasification, a technology that uses an electrical arc to generate temperatures exceeding 4,000 degrees Celsius, hot enough to dissociate even the most recalcitrant waste into its elemental components. The syngas produced, primarily hydrogen and carbon monoxide, can be cleaned of contaminants such as dioxins and heavy metals, then combusted in a combined cycle turbine to generate electricity with efficiencies approaching 40%. The United Nations Industrial Development Organization, UNIDO, reports that plasma gasification plants operating in Italy and Japan have achieved net negative carbon footprints because the captured CO2 is sequestered or utilized in synthetic fuel production. While the capital costs of plasma reactors remain high, often in the range of $200 to $300 million for a 100-ton per day facility, their ability to process municipal solid waste, hazardous industrial residues, and even contaminated soils without creating ash or slag that must be landfilled makes them a compelling alternative to reckless disposal in volcanic vents. Biological treatments, too, have matured from niche applications to mainstream waste management tools. Anaerobic digestion of organic waste, food scraps, agricultural residues, and even certain paper products produces biogas composed of roughly 60% methane and 40% carbon dioxide. When captured and purified, this biogas can replace natural gas for heating, cooking, or power generation, offsetting fossil fuel consumption. In Germany, the Biogas Act of 2015 spurred the construction of more than 8,000 digestion plants, which together process over 30% of the nation's agricultural waste and generate roughly 15 gigawatts of renewable electricity, enough to power 2 million homes. Moreover, the digestate, a nutrient-rich slurry, can be applied to soils as a natural fertilizer, closing the loop between waste and agriculture without emitting the nitrogen oxides that would accompany synthetic fertilizer production. For electronic waste, which contains a cocktail of valuable metals and hazardous substances, urban mining initiatives have begun to extract copper, gold, palladium, and rare earth elements with far lower environmental impact than conventional mining. The Basel Convention's recent amendment on e-waste encourages the development of green recovery facilities that employ hydrometallurgical leaching using biodegradable solvents. In a pilot program in Sweden, researchers demonstrated that a closed-loop leaching process could recover 92% of gold from printed circuit boards while reducing acid consumption by 80% compared with traditional cyanide leaching. The extracted metals can then re-enter the manufacturing supply chain, diminishing the demand for virgin ore extraction, which is often accompanied by deforestation, water pollution, and carbon emissions. A critical component of any future-oriented waste management system is the integration of digital platforms that provide real-time data on waste generation, collection routes, and processing efficiency. The Internet of Things, IoT, sensors embedded in dumpsters can alert municipal services when bins reach capacity, optimizing collection schedules and reducing fuel consumption for trucks. Machine learning algorithms can predict seasonal fluctuations in waste streams, allowing recyclers to adjust capacity and avoid bottlenecks. In South Korea, a nationwide smart bin network reduced the average collection distance per truck by 18%, saving an estimated 1.2 million tons of CO2 emissions per year. When combined with blockchain-based tracking of material provenance, such technologies also increase transparency for consumers, who can verify that the products they purchase are part of a verified circular supply chain. Policy frameworks continue to shape the trajectory of these alternatives. The European Union's Waste Framework Directive, revised in 2023, sets a binding target of 65% of municipal waste to be recycled or prepared for reuse by 2035. To meet this goal, member states are required to implement separate collection for plastic films, textiles, and bio-based materials, and to phase out landfilling of mixed waste. Meanwhile, the United Nations Sustainable Development Goal 12, Responsible Consumption and Production, calls for a tenfold increase in recycling rates globally by 2030. Achieving these ambitions will demand coordinated action across governments, industry, and civil society, including incentives for product design that facilitates disassembly, extended warranties that encourage repair, and public awareness campaigns that shift consumer behavior away from single-use items. Education plays an equally vital role. In many regions, the lack of knowledge about proper segregation leads to contamination that renders entire batches of recyclable material unusable. Community-based initiatives, such as Japan's Recycle by Hand workshops, teach residents to separate plastics by resin type, flatten cardboard, and rinse containers before disposal. These low-tech interventions have measurable effects. A study in Osaka showed that contamination rates in mixed plastic streams fell from 24% to under 8% after a year of targeted outreach, effectively increasing the volume of material that could be fed into high-grade recycling loops. Investments in research and development are also essential to keep pace with the evolving composition of waste. Emerging polymers, biodegradable plastics, polymer composites reinforced with natural fibers, and nanomaterial-enhanced films present new challenges for existing recycling infrastructure. Universities across the United States, Europe, and Asia are exploring catalytic depolymerization pathways that can selectively break down these novel polymers without generating harmful byproducts. The National Science Foundation's Future of Plastics initiative, for instance, has awarded $150 million to multidisciplinary teams working on enzyme-based recycling, which could, in theory, achieve near-complete conversion of mixed plastic waste into monomers at ambient temperature. The economic incentives for adopting these safer alternatives are becoming increasingly compelling. A 2022 report by the World Bank estimated that every dollar invested in circular economy initiatives yields a return of $2.60 through reduced material costs, lower waste management expenses, and avoided environmental damage. In the United Kingdom, a carbon pricing scheme that levied £18 per ton of CO2 on landfill disposal prompted a 30% shift from landfill to energy recovery facilities within 3 years, saving an estimated 4.5 million tons of CO2 equivalents. Companies that embrace closed-loop practices also benefit from brand differentiation. Consumer surveys from Nielsen indicate that 73% of shoppers are willing to pay a premium for products with verified sustainable packaging. In the long term, the convergence of these technological, policy, and societal shifts points toward a waste management paradigm that is resilient, adaptable, and fundamentally decoupled from the planet's most volatile geological processes. By capturing waste before it becomes an environmental liability, converting it into valuable inputs, and ensuring that each step is monitored and controlled, we can build a system that not only reduces the volume of material entering the environment, but also creates economic opportunities and jobs in new, high-tech sectors. The transition will not be instantaneous. There will be periods of adjustment as legacy infrastructure is retrofitted or retired, and as industries retool their supply chains. But the trajectory is already clear. The future belongs to solutions that are scientifically sound, economically viable, and socially acceptable, rather than to speculative schemes that gamble with the Earth's inner heat. When we look ahead, the picture that emerges is one where waste streams are continuously fed into a network of specialized facilities, each designed to handle a particular class of material under optimal conditions. For instance, a city's organic fraction might be diverted to anaerobic digesters located on the outskirts, generating biogas that powers local public transportation. Plastics and composites could travel to a regional chemical recycling hub where catalysts and renewable electricity drive depolymerization, producing feedstocks for new packaging. Metals and electronic components would flow to urban mining centers equipped with closed-loop leaching processes, extracting precious elements without contaminating water sources. Residual, non-recyclable waste would be treated in plasma gasifiers that produce clean syngas for electricity generation, with emissions scrubbed to meet or exceed the strictest environmental standards. The net effect is a virtuous cycle in which material loss is minimized, energy is reclaimed, and emissions are curbed. Such an integrated approach also offers the flexibility to adapt to future challenges, such as the anticipated rise in e-waste as the world becomes ever more digitized, or the emergence of novel materials whose end-of-life pathways are not yet defined. By investing in modular, upgradable facilities and fostering collaborations between academia, industry, and government, we can ensure that the system remains responsive to new scientific discoveries and market dynamics. The emphasis shifts from a one-off disposal event, whether in a landfill, an incinerator, or a volcanic crater, to a continuous stewardship model in which every product is tracked, recovered, and reintegrated. Finally, the social dimension cannot be overlooked. Communities that have historically relied on informal waste picking often find new livelihoods in formal recycling and material recovery enterprises. In Brazil's São Paulo, a municipal program that formalized waste picker cooperatives led to a 12% increase in recycling rates while providing health insurance and stable wages to over 10,000 workers. When people see tangible benefits, cleaner neighborhoods, new jobs, reduced pollution, the cultural acceptance of circular practices deepens, creating a feedback loop that strengthens the overall system. In sum, the path forward is illuminated by a constellation of proven and emerging technologies, reinforced by robust policy instruments and buoyed by public engagement. By leveraging mechanical, chemical, biological, and plasma-based treatments in a coordinated network, we can handle the world's waste safely and efficiently, eliminating the need to gamble with the planet's own volcanic activity. This strategic pivot not only safeguards ecosystems and public health, but also aligns economic growth with environmental responsibility, charting a course toward a truly sustainable future.